Let's look at the electronegativity of different elements and the polarity that results from combining these elements together. So in addition to drawing a polar bond, I'm going to go ahead and draw all three of these. A covalent bond is a shared pair of electrons. The chlorine molecule over here has the two chlorine atoms sharing a pair of electrons. So they are sharing evenly. There's no reason why one chlorine would be pulling on electrons more than another chlorine. They're evenly matched. An ionic bond is not sharing. So remember, when an ionic compound forms, the positively charged cation is missing a valence electron, or more than one. The chlorine is negatively charged. The chloride anion has an extra electron. So it's kind of like the chloride stole the electron from this sodium. There's not any sharing going on here. That's why we don't actually draw a bond. Here we have an intermediate case. We have hydrogen and chlorine sharing electrons. We have a covalent bond drawn here in this Lewis structure. So they are sharing this pair of electrons, but they are not sharing it evenly like these two chlorines are. The chlorine is pulling on the electrons more than the hydrogen is. It's more attracted to the electrons, it pulls on them more strongly. And so these electrons are being shared, but they're not being shared evenly. The electrons are spending more time around the chlorine than they are around the hydrogen. So it might be helpful to think of two kids with a toy. If you have kids who are evenly matched, each kid gets the toy for about the same amount of time. Then you could have a difference in the aggressiveness or the strength of the two kids, and you have one kid who's more aggressive or who just wants the toy more, and so they're going to be playing with the toy more than the other kid. Maybe whenever mom's looking, the other kid gets a turn, but most of the time this kid is going to have the toy. So we have sharing but unfair sharing. And then this case would be when one kid just takes the toy away from the other kid and goes off and plays somewhere else and doesn't let this other kid have a turn at all. So ionic would be not sharing, nonpolar covalent bonds are even sharing, and then polar bonds are uneven sharing. We call this polar because this molecule does not have any positive or negative end. This molecule has one end that is a little bit more negative because the electrons are spending more time closer to this end and less time closer to this end. It's not a full negative and positive charge, it's a partial negative and positive charge, so we draw it with this little lowercase delta. We can draw one end of the molecule as being partially negative and one end as being partially positive. And so there is a dipole. If you had an electric field or a magnet or something, you could line this up, whereas this one would not have any attraction to a positive or negative field because the electrons are evenly distributed and there's not a positive or negative end. So this positive and negative end is called a dipole. A lot of times we could draw this with an arrow to show which direction the electrons are being pulled, and maybe with a little plus at the opposite end to notice that this end is where the electrons are missing, this end is where the electrons are being pulled, and so this arrow is commonly how you would denote a polar bond. How do we know that chlorine is pulling on the electrons more than hydrogen? So this is expressed as a property called electronegativity, an arbitrary scale that a scientist, Linus Pauling, invented. He just ranked these elements from 0 to 4 and rated how strongly they pulled on shared electrons. And electronegativity increases going up and to the right of the periodic table. I'll show you that in your Chem Libre text. Alright, I just wanted to show you a table of electronegativity values that's in your Chem Libre text. We don't need to memorize this, I just wanted to point out that it is here. And also that the electronegativity follows the same trend that the ionization energy does. So going from left to right across the periodic table, the ionization energy increases. It's harder to pull electrons away from the elements on this side, and that is also reflected by the electronegativity. So these elements over to the right pull on the electrons more strongly compared to the ones on the left. Also, the ones at the top of the periodic table pull more strongly than the ones at the bottom. So it's increasing electronegativity going up and to the right, similar to the ionization energy. So once you know how strongly an element is pulling on its electrons, what matters is really the difference. So chlorine has the same electronegativity in both of these compounds, but in this compound it's going to be pulling them electrons away from hydrogen, and in this one it's not going to be able to. So this is a general guide. I especially wanted to point out here that sometimes you will have ionic compounds that have less than a 1.9 difference. We'll see that down below in one of our examples. So if you have a metal and a non-metal, then even if the difference between them is only 1.8 or 1.7, that would still be an ionic compound. I have gone ahead and copied down from the LibreText table the values for the electronegativities of these different elements in this problem. And that's how we are going to decide what type of bond these form. Of course, we have a metal, calcium, and a non-metal, oxygen. And so this is going to be an ionic bond. We knew that before we learned about electronegativity, and then we'll just take the absolute value of the difference here. It's confirmed by the difference in electronegativities that we see. The difference between these electronegativity values is 2.5, which falls into the ionic range. For carbon and bromine, the difference is only 0.3. So this is a nonpolar bond. For oxygen and hydrogen, the difference is 1.4. And that's a pretty big difference. So we have a polar covalent bond. And I've been forgetting to do this, but we got to tell where the positive and the negative are. Oxygen is pulling on the electrons more, so this one is going to be partially negative. The hydrogen is going to be partially positive. Oxygen and hydrogen have such a big difference that molecules that have OH groups are extrapolar. So we'll learn about that. We'll learn about hydrogen bonding at a couple pages from now. So calcium is the cation, I'll put a plus here, and oxygen is the anion, so I'll put a minus here. Of course, they're +2 and -2, but I'll just put the positive and negative here. So the difference between carbon and hydrogen is 0.4. This is pretty even sharing. This counts as nonpolar, and that's something important to remember, that molecules that only have carbon and hydrogen in them, also called hydrocarbons, those molecules are very nonpolar. They are greasy, oily, they don't dissolve in water. So that's something very important to remember about the chemistry of hydrocarbons. The difference between carbon and oxygen electronegativity is 1.0. So this is a polar covalent, and oxygen is pulling more strongly, so that would be partially negative. The carbon would be partially positive. We already know that lithium and chlorine make an ionic bond. They do have a pretty big difference in electronegativity. Lithium is the cation and chlorine is the anion. Bromine and bromine have no difference between them. So this is a nonpolar bond. Let's take a look at these two compounds together, actually these three. So we have sodium and bromine, lithium and bromine, lithium and chlorine. All of these are metal and non-metal. And so even though the differences between these electronegativities are a little bit larger, 1.9 and 2.0, this one at 1.8, we know that lithium and bromine form an ionic compound. We know that lithium makes a positively charged ion and bromine can make a negatively charged ion, just like sodium and bromine here. So these compounds are both ionic, just like this one was. Don't let the electronegativity throw you off from things that we already know about metal and nonmetals. I want to take a look at some compounds that have polyatomic ions in them. We've looked at some of the Lewis structures of these ions before, ammonium, nitrate, and the Lewis structures show that the nitrogen and oxygen are sharing electrons. We have covalent bonds here within that polyatomic ion and within ammonia. However, the overall structure of ammonium is an ion. The same thing with nitrate, the same thing with sulfate. When ionic compounds dissolve in water, we'll learn more about this in chapter 9, but the ions get solvated by the water. And so the cations and the anions separate from each other, they dissociate, and they get surrounded by water molecules. These red things are water molecules, and then we have some blue cations and some green anions. Okay, I accidentally reversed my color coding here, but we have the polyatomic cation, ammonium, separating from the anion, the chloride ion. So the ammonium separates from the chloride when you dissolve it in water, but the hydrogens do not separate from the nitrogen. They stay together as a polyatomic cation. Over here we have a polyatomic anion. The nitrogens and oxygens are joined by covalent bonds. They stay together, but the nitrate groups separate from the calcium cation. And over here we have the sulfate anion separating from the zinc cation. So let's talk about the overall polarity of a molecule. We've talked about bonds between one element and another being polar or nonpolar. So covalent bonds we're talking about here, not ionic. It is possible for a structure to have polar bonds but overall be a nonpolar molecule. In order to be a polar molecule and have one end of the molecule being positive and one end of the molecule being negative, we have to both have polar bonds that pull the electron in one direction, and then overall the shape has to be asymmetric. Let's go ahead and see if we can illustrate it on this example below. All right, so let's go ahead and draw bond dipole moments in blue. So carbon, on the previous page, we saw that a carbon-oxygen bond is polar. The oxygen is pulling the electrons away from the carbon. Let's draw that bond being polar. And then this bond is also polar. However, these two polar bonds are pulling in opposite directions, so they cancel each other out. This molecule is symmetric. So overall, the molecule is nonpolar. There's no overall dipole. And that is because it is a symmetric molecule. In contrast, this molecule has the oxygen pulling electrons away from carbon, but the sulfur is not pulling in the opposite direction very much. These both have 2.5 electronegativity, so they're more evenly matched. So we don't have this second dipole counteracting the first dipole. We only have a pull in one direction. So that is going to give an overall dipole for the molecule in that direction as well. We have a slightly negative end of the molecule and a slightly positive end of the molecule. So this is a polar molecule. This one has an asymmetric shape. All right, I've sort of added to this example over here. This original molecule that's in the question, boron and hydrogen have the same very similar electronegativity, 2.0 and 2.1. So these bonds are nonpolar. Also, this shape is symmetric. So this is definitely a nonpolar molecule. This other example, boron with 3 fluorines, these are definitely polar bonds. The fluorine is way more electronegative than boron, but since it has a symmetric shape, all of these dipoles are pulling the electrons in symmetric directions around the molecule, and so the dipoles cancel each other out. So this molecule is also nonpolar. So this symmetric shape with nonpolar bonds or with polar bonds will yield a nonpolar molecule because there's no overall dipole pulling in one specific direction away from another direction. Here we have an asymmetric shape. It's symmetric around the nitrogen, but it's not that symmetric up and down. So we have the electrons being pulled away from hydrogen towards nitrogen. We have a polar bond, an electronegativity difference. And so left to right, all around here, they're canceling each other out, but up and down, they are not canceling each other out. So each of these hydrogen-nitrogen bonds is pulling the electrons a little bit up. Like if you picture a table here, they're pulling it a little bit up away from the table. So overall, there's a dipole making this end of the molecule a little bit negative, this end of the molecule down here a little bit positive. So this is a polar molecule as well. Here we have another example of polar bonds, chlorine pulling on the electrons more than carbon, but all of these chlorines are arranged symmetrically around the carbon atom, so they are pulling the electrons in every direction. There's not one end or another that is negative and another end that is positive. It has a symmetric shape, no overall dipole, and it is a nonpolar molecule. This one has more of an asymmetric shape because we have the chlorine pulling up and the chlorine pulling down and to the left, and we don't have pulls by these hydrogens on the electrons to counteract those pulls. So this asymmetry causes an overall dipole in this direction, sort of up and to the left. And so this is a polar molecule. It has a little bit of a negative end on this end and a little bit of a positive end on this end. You can play around with this a little bit on the simulator, but it only works with these 3 atom molecules. It works with a 2-atom molecule as well, but for the ability for something to have polar bonds but a non-polar molecule, I think you need 3 atoms. So there is a cool simulator that lets you play with these molecules and shapes and the polarity of the bonds. I wanted to show you in Module 4 on Canvas the Fun with Molecule Shape and Polarity page. It has a simulation. Besides the one about shape, the next one is about polarity of molecules. So this is fun to play around with a little bit. You can view the dipole as an arrow. You can even view the little partial charges here, the delta plus and the delta minus. You can see how the bond is becoming either more covalent, more nonpolar, or more ionic. So here we have atom B being in the middle as far as electronegativity, atom A being less. You can make them more even. The dipole disappears. You can make A more electronegative, the dipole goes the other way. You can see what happens if you have an electric field. You can turn that on. So the positively charged plate is going to attract the negatively charged end. The negatively charged plate will attract the positively charged end. If you switch the electronegativity, it's going to flip over. If you make it so that there isn't a dipole, then it won't be attracted at all. You can also try it with 3 atoms. Let's do that. So you can look at the bond dipoles in black and then the overall molecule dipole in yellow. And you can look at the partial charges. even for polar bonds, if overall the molecule is symmetric, the dipoles can cancel each other out, and overall there isn't a molecular dipole. Here we have a less symmetric shape, and so both of these left to right is canceling out, but up and down is not canceling out. Overall there is a dipole in the vertical direction, kind of up here. Even with this asymmetric shape, if all of these atoms had the same electronegativity, we wouldn't have any dipoles at all, either on the bond or on the molecule. And then that would not be attracted to an electric field. If we go back to the original molecule, we do have this attraction to the electric field. Let's take a look at how the polarity of molecules influences their properties, the visible properties that you can see. And the reason for this is that when you have positive and negative charges, say with a polar molecule, they can be more attracted to each other. So these brown molecules are polar molecules, but they have a slightly negative and slightly positive end, and so they get attracted to the next molecule, positive and lines up with negative, and so forth. So these can stick together a little bit more. These purple molecules are nonpolar molecules. There's no positive or negative end, so they're just sort of randomly floating around next to each other. So the attraction between two different molecules is an intermolecular attraction, attraction between separate molecules. And the strength of this interaction increases going up this chart. So the weakest attraction is these purple molecules. The nonpolar compounds don't have a permanently positive or negative end, and so they don't stick together quite as strongly. Polar molecules have this positive and negative end that can stick to each other, so they can be attracted more strongly. An extreme case of this is hydrogen bonding, which is like superpolar. If a molecule has an OH or an NH group in it, then it can have even stronger polarity. And then an ionic compound is not really made of molecules, so talking about this as an intermolecular attraction is a little bit strange, but a full negative and positive charge are attracted more strongly than a partial negative and positive charge in a polar molecule would be. So it is a more strong interaction because it's a full negative and positive charge versus partial versus not really existing. And so we have strongest on top, weakest on the bottom. The strength of this interaction causes an increase in boiling and melting point, because the more strongly these molecules are attracted to each other, the harder it is to melt their crystal structure, the harder it is to boil them and get them flying around as gas molecules away from each other. Stronger interactions will cause the compounds to have higher boiling points and melting points. Water is like all hydrogen bond all the time, which means that water has very strong interactions with other water molecules. And so it does not want to break up its interaction with other water molecules unless it's for something just as strong or even stronger. So something that is ionic, salt, will dissolve very well in water. Something that is hydrogen bonded like sugar will dissolve very well in water. Something that is nonpolar like oil or kerosene, hydrocarbons we mentioned, things with hydrogen and carbon only are nonpolar molecules. These will not dissolve very well in water because water does not want to interact with these as much as it wants to interact with itself. So it won't make room for these compounds to dissolve in it. Let's take a look at using this information to decide which of these compounds would have the highest and lowest boiling point. We looked at the polarity of the CO2 molecule before and we decided it was nonpolar. We just mentioned water as being able to hydrogen bond. And we know that sodium chloride is an ionic compound. Ionic compounds have the strongest interaction. So this would have the highest boiling point. And then the next strongest interaction is the hydrogen bonding water. So this would have the middle. And then the nonpolar molecule would have the lowest boiling point. So if we're supposed to actually rank them, this would be number 1, this would be number 2, and number 3. Here we have lithium nitrate, an ionic compound, bromine being a nonpolar compound because the bromine atoms share the electrons evenly. And so the more soluble compound would definitely be the ionic compound. So a higher melting point, we have a hydrocarbon here, something that only has carbon and hydrogen. So that is a nonpolar substance. We have something with NH groups. So that is not only polar, but it's capable of hydrogen bonding. So this is the compound that has a stronger intermolecular attraction and a higher melting point. Here we have an ionic compound being compared with a nonpolar compound. If you remember from the previous page, this molecule has a symmetric shape, so the polar bonds are evenly arranged around the molecule. Overall, the molecule is nonpolar. So the ionic compound would have definitely a higher boiling point.